Hello everyone, today let's take a look at QP41 where we're just proving some useful facts about variance that are going to come in useful later, right? So let x1 all the way up to xn be real random valued variables with finite second moments, and we have a and b that are constants, and we have to prove the following. So first of all, in part A, we're going to show that the variance of a times our random variable x plus b, so a and b are constants, is just going to be equal to a squared times the variance of x. And we can basically solve all of these just by doing a lot of algebra using the definition of variance. In the definition of variance, it's just the average squared distance from the mean, so the expected value of x minus the expected value of x in here, all of that squared. So therefore, part A shouldn't be too hard. We're just going to plug this in where we see x, right? So the variance of ax plus b is just going to be equal to, well, the expected value of ax plus b. So expected value of ax plus b right here minus the expected value of ax plus b, and then that is all going to be squared like so. Okay, so now for this term right here, we already showed linearity of expectation in quantipose number 92. We know that this is just going to be equal to a times e of x, basically, plus b. So when I plug this in right here, I'm just going to get a term that looks like this. And now we can distribute this negative sign right here. When we do so, we're going to get negative a times e of x, and then we're going to have a negative b here as well. Now you can see we have a positive b and a negative b, so those are going to cancel right there. So when we cancel out those b's, now we're going to be left with this term right here. And now you can see we can pull a common factor of a out of here. So we're just going to have x minus e of x on the inside, and we'll have a on the outside, and then this whole term right here will be squared. So we're multiplying these two terms inside of my square, so that's just going to be equal to, when we rewrite it, this whole term is going to be the expected value of a squared, and then we have times x minus the expected value of x with all of that squared. And then again, linearity of expectation here, we can just pull the a squared out. This is just going to be equal to a squared times the expected value of x minus the expected value of x, where all of that is squared on the inside. And then this right here is just the definition of the variance of x, remember? This is just the definition. So basically this is just going to be equal to a squared times the variance of x, which is exactly what we were trying to show. So when I multiply a random variable x by a constant and I take the variance of that, it's going to end up being a squared times the variance of the random variable. And when I add a constant, it's just not going to matter, right? Which shouldn't affect the variance, right, intuitively. This all makes sense because if I have a distribution of probabilities that x can take and then I add a constant to it, I'm just going to be shifting this whole thing over by some amount, right? But it's still going to have the same shape, so I still should have the same distance away from the mean, right? So that's why the addition of this constant b right here didn't show up in this term over here intuitively. And now for this term, if we multiply by a, let's say this point right here was like 1 and then this point here was 2, and we multiply everything by 10, well, that would spread out our curve, right? Basically the same point that 1 used to be, now it's going to be at 10, and where 2 used to be, it's going to be 20 now. So the old difference was 2 minus 1 equals 1, and now the difference is 10, right? So we're multiplying the spread by basically a factor of 10, but the variance is the squared distance of the spread, right? So it makes sense that this would now be increasing by a factor of a squared. So that's part A, and now let's go into part B, which is probably the trickiest out of all of these, right? Part B here. So now in part B, if we're taking the variance of a sum of random variables, unlike linearity of expectation, it's not going to be linear unless these all are independent, right? So not necessarily independent, you have this formula right here, and then part C, we'll see when they're independent. Instead, we're going to have the sum of all these variances, and then we're going to have these extra terms, right? 2 times all of the covariances. So let's show how we derive that from this, using basically just the definition of variance. Okay, so in my definition of variance, all I've done down here is I've plugged in my basically x value, right? I'm just plugging in here, and then I get this equation right here. Okay, first thing to notice right here, I'm taking the expectation of a sum of random variables. We know linearity of expectation, right? We can just write that as the sum of the expectation, regardless of dependence or independence. Now we're taking a sum over the exact same thing right here as we are right here. So we can just write this in terms of one sum, which I'll do down here. So this is what I get. You can see I've combined these two sums now. Now in the inside of our sum, we have xi minus the expected value of xi, which are two values right here. And then we are taking the sum over all of these, and then we're squaring this whole sum, right? Sorry for so many parentheses. But if we take a look more closely at this term, it's very close to being the variance, but it's not, because this square is not inside of here. It's not inside of this sum. If it were in that case, then we just have the variances summed up, but it's outside of the sum, right? We're taking the sum first, and then we're squaring that, right? So now let's just start expanding this term a little bit just to see what's going on, because it's a little confusing. Well, when we start, we have x1 minus the expected value of x1. That's for the first term of the sum right here. And then we're going to iterate up to 2. So we add on basically x2 minus the expected value of x2. Then we can iterate once again, and we're going to have x3 minus the expected value of x3, and etc. all the way up to n, basically, is our ending point. So we keep on adding up until our final term is going to be x sub n minus the expected value of x sub n. And now we're running out of room here, so I'm going to make a new page. Okay, so to continue, I have all these terms right here, and now I'm squaring them, right? Once I've summed them all up on the inside, now I'm taking the square, so I have this all squared. So what we're doing here is we're taking this whole term right here and we're multiplying it by itself. So for this term, let's just start by looking at this term. It's going to get multiplied by itself and every single other one of these terms, right? So it's going to have x1 minus the expected value of x1, and then that's going to be squared. And then we're going to add on all the pairwise stuff, right? And then I'm going to have all my other pairwise terms, right? x1 minus the expected value of x1 times x2 minus the expected value of x2, x1 minus the expected value of x1 times x3 minus the expected value of x3, and so on. Now for the next term in our equation right here, we're going to do the same pattern, right? We're going to have x2 minus the expected value of x2, and that's all going to be squared when we multiply this one by itself, and then we're going to multiply it by all of our other terms, so all of our pairwises. We get plus x2 minus the expected value of x2, then that's going to be multiplied by every other one, right? x1 minus the expected value of x1, x3 minus the expected value of x3, so on. You can see that these two terms are going to be the same. Well, there's only going to be one of these, right? This is just the binomial theorem. We proved all this back in combinatorics, but basically once you go through every single term, you're going to realize that you have one of all of these squared terms, right? When we have the same term multiplied by itself, and we have two of basically all of these pairwise terms. This is again just the binomial theorem, so we can basically just group all of these terms that are multiplied by themselves, and then we can group the terms that are pairwise, right? So let's do that. So in general, this is what that's going to look like as a formula, right? We're summing up over I equals 1 to n of basically all of our singular terms, right? When I is equal to j, so we have xi minus the expected value of xi squared, right? All of these right here. And then this term over here is going to be all of our pairwise, right? When I is not equal to j, right? Because when I was equal to j, we had these over here. So we're summing up from I equals 1 to n and j equals 1 to n of basically this right here. So again, when I is not equal to j, so I might be 1 here, and then j might be 2, or I might be 1, and then j might be 3, and we're summing up over all of these. 4, I is 1, j is 5, I is 1, j is 6, I is 1, j is all the way up to n. Then once we have all of those, I is going to increment to 2, and then we're going to have j equals 1, and then again, j is not equal to I, so j skips 2, and it goes to 3, and then it goes to 4, and then it goes to 5, and then it goes all the way up to n again, right? And then I will iterate to 3, and we'll have the same pattern. But again, we're going to be double counting these terms right here. For instance, when I equals 1 and j equals 2, we're going to count that. And then we're also going to have I equals 2 and j equals 1, right? So we're counting the same term twice, right? Because these are basically identical. So since we're summing up all these terms twice, it's going to be simpler to write this in terms of one sum, right? So we could pull this 2 out, since we know we're going to be summing up every term twice. And then we could just have I going from 1. So I is less than or equal to 1, which is less than j, right? And j is going up to n at both I and j are. So now instead of the double sum, we'd be counting 2 times when I equals 1 and then j equals 2, right? That satisfies this condition. And then when I equals 1 and j equals 3, 2 times that, right? And then when I equals 1 and j equals 4, 2 times that. And then the iteration when I equals 1 would be complete. We go all the way up to I is n minus 1 and j is n, right? Because I has to be less than j right here. And then we'd have I increment to 2, and then j would be greater than that, right? So we have 2 and 3 and 2 and 4. And now we're not double counting everything, but we're multiplying everything by 2. We just express it as a single sum, right? This is all binomial theorem stuff, right? From the combinatorics roadmap. There's a section on that where we talked about that more. Okay, but at the end of the day, this is what we got right here. This whole term right here was equal to this one right here. And then basically to get the variance, right, we were taking the expected value of that term, right? So let's take the expected value of this here. And again, by linearity of expectation, it behaves just like you'd expect a sum to behave, right? It's linear, so we just have this right here. We can pull the expectation inside here, and we can distribute it to this term over here. So we're going to have 2 times, well, the expected value of this right here. Let me write it in, the expected value of this inside of here. And now the expected value of x sub I minus the expected value of x sub I all squared. What is that? Well, that's just the definition of variance. So this term right here is just going to be the sum from I equals 1 to n of the variance of x sub I. And then the expected value of x sub I minus the expected value of x sub I times x sub j minus the expected value of x sub j, where I and j are not equal, is just the covariance. This right here is the covariance of x sub I with x sub j. So then this whole term right here, again, is just going to be equal to, well, 2 times the sum from 1 less than or equal to I, which is less than j, and j is going up to n of the covariance of x sub I comma x sub j. Then again, we're summing these two terms up. I'm not sure why this one's red. I don't know why I went with the red here. Let's make this one white. So I don't think, let's go color white. So this whole thing right here was equal to the variance of basically the sum from I equals 1 to n of x sub I. So we've proved what we originally set out to, right? That was exactly this equation right here. This should be j less than or equal to n because j can go up to n. So I guess it would have been more appropriate to do it like so, right? Because we're implying that j is going up to n, but I is going up to n minus 1, right? Because we're doing the ordered pairs here. But I still meant the same thing. But basically now in number C, or letter C, right, we have independent simplification. So when these are independent, we need to show that the variance of this sum is just equal to the sum of the variances. So now down here, we are going to have the exact same thing, right? But now we are under the assumption that all these x sub i's are independent of each other. So in part B, this is the general case when the xi's are not assumed to be independent or dependent, but now we have them independent, right? I made a new page now, so let's just show basically that this term goes away when they are independent. Well, to do that, all you have to do is notice that when they're independent, the covariance is 0, but why? Well, the covariance of x sub I and x sub j is just defined as the expected value of x sub I minus the expected value of x sub I, basically just times the expected value, x sub j minus the expected value of x sub j. If we just look at this term right here inside the expectation and we multiply it out, right, we're going to get xi times xj, and then we're going to have plus the expected value of xi times the expected value of x sub j. And then our other terms are going to be, let me make some more room, well, they're going to be minus the expected value of x sub I times x sub j, and then we're going to get minus the expected value of x sub j times x sub I. And then when you take the expected value of this term right here, because this inside was just all of this, and then we need to take the expected value of that, we can use linearity of expectation, right? It's just going to distribute over the addition. So we have expected value here. We have the expected value of this term right here, which I can't draw in. Now the expected value of the expected value of x sub I times the expected value of x sub j, well, the expected value over the same stuff is not going to change what this is right here. But when I take the expected value of the expected value of xi, it's not going to change that, but it is going to change this right here. It's going to be the expected value of x sub j. And same over here, linearity of expectation. The expected value of x sub j is a constant with respect to this expected value out here. So we can just distribute it to this x sub I that does not have an expected value yet, right? The expected value of x sub I right there. Now these terms right here are all the same. So we're subtracting it twice and we're adding it once. So we're going to be left with a net of negative that term right there. So the expected value of x sub I times the expected value of x sub j. And then over here, we're just going to have the expected value of x sub I times x sub j. Now we still haven't used independence yet, but we know from QP number 92 that the expected value of x sub I times x sub j when they're both inside this expected value can only, when they're independent, be written as basically the expected value of x sub I times the expected value of x sub j. That's when we can distribute it. That was QP 92 part B. So now we're just left with that term minus itself. These are exactly equal. So this is just going to be equal to 0. So all of our covariances here are going to be equal to 0, and that's why this term goes away when they're independent, because of this property right here. Therefore, when all of these variables are independent, x1, x2, x3, all the way up to xn, we're going to have this property right here. The variance is just going to be equal to the sum of variances, right? Which is basically linearity of variance, but they have to be independent. That's because the covariance between xi and xj, which is another useful fact to know, is equal to 0 when they're independent. So that solves all three problems of these. We proved everything just using a lot of algebra basically. And these are probably the three most useful things about variance to know, right? These three right here. Another fact that directly comes from part A is that the variance of negative x is equal to the variance of x. That's because we're essentially multiplying x here by -1, so our a value, and we know that we're just going to pull out the a squared in that case, so that's just going to give us 1 times the variance of x, right, when a is -1. So this comes directly from that and other things too, right? The variance of 1 minus x is equal to the variance of x, everything like that. So yeah, all these things are very useful to know right here.